the time's up, so let's start the first talk of this afternoon in Korean time session for actions. So first the speaker is Pira Simakajin, correct?
Simakajin, yes.
Okay, so he will talk about pre-modal gravitational wave revealed by a spinning action. So let's start.
Okay, so hello everyone. Okay, so today, first of all, I would like to thank organizer for giving me a chance to talk about this work in progress. So this is a work in collaboration with Jan Gotenua, now the postdoc in Tel Aviv, and Jardine Sermont. Okay, so in the future, we know that we have many experiments that could probe the fraction of energy density in gravitational waves over many frequency range. And for example, we have pulsar timing arrays like SKA and nanograph, and we have laser interferometers like DISA in space and Einstein telescope or Cosmic Explorer on Earth. And from the theoretical side, the most conservative stochastic signal that we should expect is the one coming from quantum fluctuation during inflation. So as shown here in the orange curve, we see that typically the amplitude of this signal is typically small, and it could be barely probed by any of the experiments in the future. However, still, this spectrum is very interesting because this comes from quantum fluctuation inflation, which continuously entering the horizon at late times. And this will source it will be a long-lasting source of gravitational waves. And the spectrum of this will span a broad range of frequencies. And if we be able to detect them, we can use it to trace the evolution of the universe from high to low frequency direction. So as shown here, the spectrum has a nice flat shape. This is due to the usual assumption that we usually use, that we have the standard model radiation era from the BBN scale up to the inflationary scale. However, this may not be true because in many interesting particle physics model, we can have the non-standard cosmological history. For example, we can have the matter era at some early times, or we can have the so-called kinesion eras. So with this modified cosmological history, this will lead to the distortion on the Gaussian spectrum from inflation. For example, the matter era will lead to the red tilt on the spectrum, where kinesion will enhance the Gaussian spectrum and generate blue tilt. And this is very interesting for Gaussian wave from inflation because they will increase the detectability of the signal by many order of magnitude. So now let's focus on kinesion. What is kinesion? So the simplest scenario for kinesion is that when we have the scalar field that roll very fast. So this can happen, for example, after the slow inflation, when the scalar field roll to the point where the potential is very steep. So if this scalar field dominates the universe with some large kinetic energy, we will call this the kinesion eras. So in these simple scenarios, the modified cosmological history will look like this. So we start with the inflation, then it followed by kinesion era at some high energy scale. At some point, the universe will heat into the standard model radiation. So with this modified cosmological history, this will lead to the modified Gaussian spectrum from inflation. So at high frequency here, we have enhancement from kinesion. At some point, universe will heat, and then we have back this flat part coming from the radiation era. So as we can see here, kinesion will enhance the Gaussian wave from inflation by many order of magnitude. And this can cause problem because Gaussian wave will act as an extra radiation. And if too much of them present at the time of CMB or BBN, this will violate the extra relativistic degree of freedom bound or the N-effective bound. So this N-effective bound can be recast into the bound and amplitude of Gaussian wave as in this red region. So basically it's said that the spectrum of Gaussian wave cannot exceed around omega GW 10 to -6. So now we can play around with, like, you can consider kinesion that lasts like shorter period of time. So you can move around this reheating temperature. So you basically move this point of enhancement, or you can lower the amplitude by lowering the inflationary scale. However, as shown on the right here, in the plane inflationary scale and the reheating temperature, we see that the N-effective bound is very strong and it dominates all the detectable region of the future experiment. So from this plot, this means that the particle physics model that has the early and long kination era after inflation, we cannot have any detectable Blue-tilted signal because this will violate the Big bound. So one way out of this, one can consider the ultra high frequency experiment such that you can provide like a detectable region here in this white space. But in this work, we focus on another direction. So we will consider kination with a little bit more non-trivial structure, where kination in our case will last for a short period of time, such that we can have the cutoff on the enhancement from kination and make this spectrum obey the Big bound. So one interesting way to do this is if we have the matter era that comes first before kination. So with this matter era, the potential spectrum will have a red tilt that cut off the blue tilted from kination era. And very interestingly, this modified cosmological history will generate a potential spectrum that has a peak shape like this, which will be a very interesting potential wave signature to search for in the future. Okay, now let's talk about another interesting story. So because this modified cosmological history, it can be generated naturally in a model that comes with the spinning axiom. So what is spinning axiom? So the spinning axiom is just an axiom, and then we go beyond the usual assumption that axiom just sit and frozen on the potential. So axiom in this case, we have some initial velocity, and this is very generic in a model of the kinetic misalignment mechanism, such as the model of Axiogenesis or the trap misalignment. So in this talk, let's just focus on the model of Axiogenesis. So in this case, we start with some complex scalar field or the Pershing scalar field. And the axiom is just the angular mode of this field. So in this case, the complex scalar field will oscillate and spinning inside a U1 symmetric potential, and it could obtain a large kinetic energy from the spinning. So let's talk about some setup first. So in this model to work, first we need the field to sit far away from the origins. So this can be done, for example, by the visitor fluctuation or negative Hubble induced mass that will drive the field away from the origins. So after the field sit somewhere at large wave, then at some point it will start to oscillate. And we assume that the scalar potential have two terms. So we have the term that is U1 symmetric, and this will induce the oscillation in the radial direction, while the rotation will be generated from my episode breaking term that will induce the gradient in the angular direction and induce the rotation. So first, here the field will sit frozen on the potential due to Hubble friction. At some point, it starts to oscillate, and it will oscillate and also rotate. So we have two directions of motion. So the field will orbit in elliptic orbit. And this elliptic orbit will redshift in size due to Hubble expansion. And sometimes, and we can show that if the potential is quadratic, then this will behave, the field will behave like a pressureless matter and could generate matter era. And now at some time later, the elliptic orbit will redshift down the potential, but it cannot redshift down to the bottom because the radial oscillation is still here. And this could generate the matter era at late times. And this will lead to the cosmological moduli problem. However, this radial motion will be naturally suppressed due to the interaction between the Pershing field and the standard model plasma. So one can show that if we allow the U1 conserving interaction, and by charge conservation, the radial motion will be damped while the rotation remains. So we are only left with the axion that is spinning. So now the orbit becomes circular, but still at this point, the field behaves like matter. This is due to the balance between kinetic energy and the potential energy of the field. So now we have this circular orbit, and this circular orbit will continuously redshift down the potential, and it will redshift down to the bottom. And this is where the potential energy of the field becomes negligible compared to the kinetic energy of the field. So at this point, we only have the axion that is spinning very fast. and its kinetic energy dominate the dynamics, and this could allow the kination era to start. Okay, so overall, let's summarize what we have in this model. So the cosmical history in this case will start with the scalar field that sits on the potential frozen and behave like dark energy. At some point, it starts to oscillate when the Hubble rate drops below the mass of the radial mode. Then it obtains the elliptic orbit. And at some time later, the interaction between the scalar field to some other field becomes effective. The radial motion will be damped and the field becomes circular. So up to this point, the field will behave like matter and could generate matter era that we want. And only when the field reaches the bottom of the potential, now so this energy scale corresponding to the kinetic energy in the spinning axiom. So kination starts from this point and it will last until the snap radiation becomes dominant again, and this will end kination. So basically in this modified cosmical history, the history of the universe, the non-standard history of the universe will be characterized by two parameters here. So the kination energy scale and the duration of kination. Okay, so the cosmical history that we have thermal radiation, matter, kination, and then back to radiation again. So to understand now the Gaussian spectrum that we distort from this scenario, we can trace this evolution back in time. So we start with the radiation at some low energy scale. So this corresponding to the low frequency in radiation wave. So we have flat path here from this radiation era. Then we go to higher frequency, to higher energy scale, then we have kination, and this generates blue tilt. Then we have red tilt again from matter era and back to flat path. This is from the radiation era at early time. So basically, this modified cosmical history will generate the peak Gaussian spectrum that has an interesting shape and could be observed in the future observatories. And from the peak here, we can read off from its frequencies, the kination energy scale, and the duration of kination. And the peak amplitude will get more and more amplified due to a longer and longer kination era. Okay, so now I only show you the spectrum for some particular case, for some particular value of the energy scale of kination and duration. So let's talk about now the ability of the future experiment in order to probe such scenarios. Okay, so I show you here the detectability plot. So in the plane kination duration and the energy scale of kination. So first in this gray band here, the kination will last too long and it will ends only after BBN. So this is inconsistent with the observation. And also in this red region, the kination will last also too long and it will enhance the Gaussian wave by many order of magnitude and make it violate the ineffective bound. Okay, but here still we have a large region that is available, and each point in this region we can have a successful story of kination and we can generate a peak Gaussian wave signature. And in this color, in any color region here, it is corresponding to the peak that can be observed in the future observatories. For example, LISA can probe 100 GeV to 100 TeV scale kination, whereas telescope and Cosmic Explorer can probe 10 to the 6 to 10 to the 9 GeV. Okay, now before conclude, I would like to emphasize that this plot is independent of the model of spinning axiom. So it can be generated, it corresponding to any model of spinning axiom, not only just this axiogenesis that I talk about. First of all, it can work also for the model of trap misalignment. So in this case, one have the axion that oscillate in some cosine potential at high energy scale. And at some point, this cosine potential vanish due to some dynamics. Then after some time later, it will trap again by another cosine at late times. And so in any spinning axiom model that can generate this kind of modified cosmical history that we have matter followed by kination, then we can generate a peak Gaussian signature that can be observed as according to this plot. Okay, so now to summarize, so we know that kination can amplify the Gaussian wave signature, the Gaussian wave signal coming from the early times. For example, the the long-lasting source of Gaussian wave, like the inflationary Gaussian wave, we get blue tilted. And kination, very interestingly, it can be generated naturally in the model of the spinning axion. And it will be short and low scale in this case because we will have matter era that come first, such that the Gaussian spectrum will get modified and will look like a peak like this, which could be observed, and we can read off from the peak the physics of the kination eras. Okay, so before closing, so this kind of dynamics of the fast spinning axion also leads to another interesting phenomenon like the axion fragmentation that we'll talk about later in this session by Philip and Chip. So thank you very much.
Thank you for the nice talk. So I found that there is some questions in chatting window. Can you read it?
Okay, so first there's a question. So said it would be natural that axion has a mass, so that matter-like behavior follow after the kination.
So do you have any
constraint on the axion mass?
Yeah.
So it would be
any constraint on the axion mass.
Okay, so this will depend on the how axion. So one constraint would be the dark matter production from this axion. If there will be, so I guess in this work it only work for axion. So after some time, the axion will the potential of the axion will turn on and it will oscillate, and it could behave like dark matter. And if the mass of this axion is too large, then it will leads to overproduction of dark matter. Okay, but this will, I think in the next talk, Philip will talk about how dark matter is produced from this kind of mechanism.
Okay. So yeah, the related question is, I wonder if the axion domination era happens sometime after.
Okay, so this would be when the axion mass is very large, and this can lead to axion domination. Yes.
Okay, good. So I have also just a short question. So this scenario also can be applicable for QCD axion.
For QCD axion, it might work. So okay, so here's a FA 10⁹, but okay, so the peak frequency will corresponding to the kination energy scale. So this is already 10⁹. So this is very much constrained by astrophysical constraint. So if we go to higher FA, then this peak will move out of this. So it will work only for some small parameter space for QCD axion.
Okay, all right. So I think, yeah, we can now move on to the next talk. So let's thank the speaker again.
Thank you.
So yeah, the second speaker is Philip Sorensen, right? Yeah. So can you change the next page?
Can I change what? Sorry.
Can you go to the next page? Yeah, to check whether or not it works well. Next page. Yeah. Okay. Good. So yeah, the second speaker is Philip. He will talk about axion dark matter from fragmentation. So let's please start.
Yeah. Okay. Thank you also to the organizers for giving me this chance to present here. I'm a PhD at the University of Hamburg and the DC Cosmology group. And I'm excited here to present some of our new results on how to open the dark matter window with axion fragmentation. Now, probably don't have to motivate Alp much here. Just suffice it to say that it's a very well-motivated class of particles. And exactly because it's so well-motivated, there's a lot of experiments searching for it. And here I have a collection of axion and axion-like particle experiments. And many of these really looks for axion dark matter. So here I have all these haloscopes in green, and all of these are searching for dark matter. So this, of course, begs the question of which of these axion, like ALPS, we can actually produce as dark matter. So that's really what I'm going to address here, how to produce this dark matter. Now, when we talk about ALP dark matter, we should of course start with the usual suspect, misalignment mechanism. So let's briefly review that first. So first, to understand misalignment, we have to point out two things. First, that the axiom gets a periodic potential, which in the case of a QCD axiom is generated by the instantons of QCD, and in the more general case of an ALP, it's generated by the confinement in some hidden sector. So that's the first point. The second point is that the expansion of the universe leads to a friction term in the equation of motion. And this really means the evolution of phi has two regimes. One in which the mass is much smaller than Hubble, in which case it's overdamped, and we say it's frozen, in which case it doesn't oscillate, doesn't redshift, it's just stuck. The other case in which the mass is large compared to Hubble, here it's oscillating and really scaling like dark matter. So the way misalignment works is that you assume that inflations give you some order 1 initial misalignment, and maybe it will be order 1, sometimes you have to tune it, but then it's held in place by Hubble friction, and as the expansion slows, Hubble becomes smaller, the mass also grows, so eventually this condition is violated and the field starts oscillating. So this oscillating condensate is really what gives you the dark matter. Now, if you produce dark matter with such a production mechanism, the dark matter relic is of course proportional to the initial misalignment angle. But also it's proportional to the decay constant Fa, which appeared in the periodic potential. And this means that if you try to go to higher Fa, which confusingly means down due to this weird convention, then you will begin to overproduce dark matter. Now you can of course compensate this by tuning towards the bottom of the peak. So if you're aiming to do this tuning, conventional misalignment can produce dark matter in this high Fa regime. But to go to lower Fa, you underproduce dark matter. And you can of course try to compensate this by tuning to the top instead. But this, of course, you need some way of motivating that tuning. And then you also introduce some instabilities there. This has been studied in something like the large misalignment mechanism, which I think Pion will briefly mention, but it requires a good degree of tuning. You can say that misalignment doesn't very naturally produce dark matter in this regime. That's of course a shame, because if we have a look here at the parameter space again, then we kind of miss all this juicy parameter space full of experiments. So it'd be very nice to have a better way of producing axion dark matter in this parameter space. So a lot of effort has been putting into finding ways that dark matter could be produced here. One way, which is much like what Pion just mentioned, is that you can try to add in some kinetic energy. And this kinetic energy, it will have the effect of delaying oscillations, which is what is essential in this axiom kinetic misalignment mechanism, which is proposed by Ko, Hall, and Heikaya. As Pion also discussed, to have this work, you need some kind of kicking mechanism that delivers this initial velocity. This could be something like an F-Dyne mechanism, the spinning axiom that Pion talked about. It can also be something more exotic like a trap misalignment, which was recently proposed by Kieler, Ringwald, and collaborators. But kinetic misalignment is really a general framework, and you just need to have the kinetic energy given by any mechanism, and then it can work. It doesn't really matter how you get the kick. So if you then assume that the field has some high initial velocity, instead of being frozen, it can really roll and pass barriers. This can happen as long as the kinetic energy is higher than the barrier height. Now, of course, Hubble friction will try to slow you. So over time, you will generally lose kinetic energy, and eventually your kinetic energy will drop below the barrier height, and you'll become trapped and begin oscillating. Now, this can happen much later than it would have started to oscillate by conventional misalignment. So because it happens later, you get less redshift, that gives you more dark matter, and that allows you to go to lower FA. So this really gives us a way of extending the parameter space into the low FA regime. Now, what we discovered in this work is that you cannot go to arbitrarily low FA, because if you try to go further in this direction, then the field will begin to experience instabilities as it passes these barriers. And this was first noticed like in the data cosmology group when they were studying real axioms, which is another kind of scalar that passes barriers. And what they really found is that these instabilities here can really break up the field. Now, this is an effect known as axiom fragmentation. It was like originally discussed in this reference from Janine Usuka and collaborators. And I won't talk about it too much because Chem has an entire talk about it, which I highly encourage you to have a look at. It's in just 20 minutes, so it's very relevant. But I can just give you the absolute minimum you need to understand. So the absolute minimum fragmentation you need to understand is that as the field passes these barriers, it experiences a periodic instability when it passes these peaks. And this periodic instability really drives the amplification of fluctuations and some corresponding to some resonant band of frequencies. So you really have fragmentation driving the amplification of these fluctuations. Now, this rapid amplification corresponds to particle production, and this particle production really drains the energy out of the homogeneous mode. It acts like a friction, and it can actually stop the field. And although this is a friction, it's important to note that because the width of this frequency band is inverse to phi dot, then this really is inefficient for large phi dot, and it really becomes efficient as the field is slowed by Hubble. And if the particle production becomes more efficient in Hubble, it becomes rapid, and it can really efficiently stop the field. So what happens is something like this. You first have the field rolling, passing barriers, and then as the field slows down by Hubble, particle production by fragmentation becomes more and more efficient. Now, if this becomes efficient before it's stopped by Hubble friction, then you can really have this rapid particle production where all the kinetic energy is dumped into particles, and the field is stopped. Now, in contrast to kinetic misalignment, all these fluctuations, they backreact on the scalar on the zero mode and really completely randomizes the field. It really destroys any notion of a homogeneous mode. So this really replaces kinetic misalignment, preventing it by randomizing the field, and instead produces a dark matter relic in the form of a gas with some momentum spectrum. It's interesting that although this production mechanism is entirely distinct from kinetic misalignment, the dark matter relic is really similar. And this is related to a symmetry argument because it appears that both have their dark matter relic fixed by the PQ charge, the fixed Peter-Quinn charge, which really corresponds to the rolling or the rotation of this axion field. So there appears to be some symmetry argument linking these two. But it's despite this, it's important to note that it's entirely distinct. You do not have a oscillating homogeneous mode. You have a gas of axion particles with some momentum spectrum. Now, knowing that this effect exists, we can look at what kind of dark matter this can produce. How we can open the window here. Now, the area where fragmentation is effective is really the low FA regime. So you can see here that in this regime, dark matter can be produced by fragmentation. And the border here is really set by where the fragmentation does not become efficient before the field is trapped. Below this, you would expect to have kinetic misalignment, but it's also interesting that in the regime, even where the field is trapped, you can still have resonant amplification of fluctuations. And what is really suppressing this in kinetic misalignment is Hubble fiction. But as you go as you delay the onset of oscillations more and more, Hubble becomes smaller compared to MA, and this protection really is weakened. So you actually end up having a regime here where fluctuations can grow even after trapping. So you really have fragmentation eating into the kinetic misalignment space here. So all of this here is now produced by fragmentation. You have a regime produced by kinetic misalignment, and then down here you must have standard misalignment. Just to give you a feel for how the parameter space looks here, I have some contours of some of the most important parameters. I have m over h, the barrier height. You have the velocity before stopping, which ranges from hundreds to tens of 100 of tens times the barrier height. And then you have the temperature where the stopping occurs. Now, it's interesting to note here that this can happen at really low temperatures. So you really end up having the lower bound on the mass being set by BBN here. So now, if we look again at the parameter space, yeah, we see we have the lower bound here from BBN. But then really all of this regime here, you can have dark matter produced by fragmentation. Here you have dark matter produced by kinetic misalignment, and here you have the dark matter produced by standard misalignment. But you can see that fragmentation can really provide axion dark matter in this experiment-rich testable regime here. So that is very nice. Like some of these experiments can not only detect an ALP particle, but actually really detect a dark matter ALP particle. So that's really nice. Specifically, if you zoom in this range here, then you can see that you could even have QCD axion dark matter, which could be detectable by experiments like Axiom. So that is, of course, very, very nice. It would be a very nice thing to see. Now, if any of these experiments really find an ALP or an axion, a QCD axion, then of course be nice to know that it's the particle produced by fragmentation. So we've been looking for some signatures that could allow us to uniquely identify this as the action of fragmentation. So one signature that has been proven viable appears to be the formation of axion mini clusters. And this is something that can happen in fragmentation because you really produce this axion gas with some calculable momentum spectrum. And then from that momentum spectrum, we can calculate the power spectrum of mini clusters. So this is still in progress. Hopefully we will have some finished results soon, but this is something that Chem will talk a bit about more. Another possible signature is the production of gravitational waves. It's not just in the way that Pion talked about in the previous lecture, but you could really have direct production of gravitational waves from parametric resonance. This is well known in the context of inflation, and it can also happen during fragmentation. This we'll also study in future work. Probably will not be part of the first paper on this topic, but it's a possible signature that we might see in the future. And of course, we're still looking for more ways to really distinguish this axion gas from that produced by kinetic misalignment. Yes, but as you see, we can really produce fragmentation can really produce axion dark matter in this testable regime, which hopefully we'll be able to see someday in the future. Okay. Yeah, I believe that's the 15 minutes of talk. So then, thank you for listening, and I believe we have some time for questions now.
Thank you for a nice talk. So question time. So is there any question about axion fragmentation?
So I have a question.
Yes.
as far as I remember, in the original kinetic misalignment mechanism, the necessity ingredient is the initial kinetic energy should be large to get large enough action dark matter.
Yes.
And I guess in this case, the initial kinetic energy must be larger than the original kinetic misalignment.
No, that's not true. Actually, it's the initial velocity is identical to that of kinetic misalignment because they produce the same relic. It's really fixed by the momentum of the field, so that is identical to that of kinetic misalignment. The difference here is that in the original misalignment paper, they neglected this growth of fluctuations. So really, this replaces kinetic misalignment in some part of parameter space. So if you try to make the setup that went into the original kinetic misalignment paper, this fragmentation will really prevent that from happening by fragmenting the field before kinetic misalignment occurs. But it works with the same initial conditions that was originally thought out for kinetic misalignment.
Well, I'm confused, but yeah. I'll think about it and email if I have further questions.
Yeah, it's really the same initial conditions that you would have expected kinetic misalignment to work for. It's just what happens here is that particle production by fragmentation becomes efficient before kinetic misalignment could take place.
So here,
feel
the
free to-
Hubble friction is inefficient, less efficient than Axiom fragmentation, right?
Hubble friction starts out being more efficient because at high velocities the resonance band is really narrow, but then as the field is slowed down by Hubble friction, the resonance band grows in width and fragmentation becomes more and more efficient. Fragmentation takes place if the friction from particle production begins to dominate that of Hubble friction, in which case it grows rapidly and really stops the field.
Yeah.
All right. So is there any other questions?
Yeah. I hope it was because it was very clear. Otherwise, Cem will probably clear up some of fragmentation. If you have a look at his talk very soon, should fit neatly into this.
So then I just have a very, very naive question about your short discussion of a gravitational wave. Can you expect some general frequency band for given example for QC detection or whatever benchmark example?
Yes, we can calculate the frequency of the signal. I must admit that I did this a while ago, and I honestly don't really remember right now where it lies. But it looks like it's a bit hard to get in the observable regime if you also want it to be dark matter. It might be more promising if you relax the constraint that the relic is dark matter. Then you might be able to move it into the detectable regime. But it looks like it's a bit of a challenge to really have the peak of the signal from parametric resonance to be in the observable range. This is why we're probably not going to include it in the first publication on this, because it's hard to both simultaneously have it be dark matter and give a gravitational wave signal. But we're still investigating whether there's some parameters in which this can work.
Okay, good. So then let's thank speaker again, and let's move on to the third speaker. So okay, so Alexio, yeah, can you share your top file or screen?
Yes. Hello. Good morning. Okay, so here it is.
And yeah, could you make a
Is
full
that
screen
visible?
and change the page? Okay, good.
That okay? Yes.
Yeah. So you will you not use? I mean, don't you use some full screen mode, or is it? I mean,
I
this
can
is
try.
good for you. I mean, if
I
this
can
is good
try, I
for
can
you, it
try.
will be.
Full screen. Not too sure, but how it works.
Yeah. Okay. I mean, it's okay. Yeah, it's okay.
Fine like this, I think.
Okay. Good. Good. So okay, the next speaker is Alexio Natari. Yeah. So he will talk about cosmic action background, the acoustic action, and the hard landing. So please start.
Okay. So thanks for being here to listen to this talk. I will basically review essentially all, I would say, all possible ways that we can use to have a cosmic background of axions. So this is very similar to the cosmic background of neutrinos, let's say. So these are hot particles, hot relics, not to be confused with the dark matter background of axions. Okay, so this is just by scatterings and decays, one can produce axions, and they contribute to, say, the effective number of neutrinos. Okay, so let's. This is work in collaboration with these people, several papers. Essentially, there are different ways one can produce axions. Here, I will focus on the QCD axion, really. So one can produce them with scatterings via gluons or quarks, leptons, and also pions. Okay, so there are very many channels for production. And the interesting part of this topic is that we can actually hope to detect this background of axions in the near future. Okay, so well, as you know very well, the axions they couple, the QCD axion couples to the gluons with this effective operator, and this produces a potential for the axion. Now the potential of course induces a mass, and the mass is related then to this coupling F. So M goes like 1 over F. Typically one shows bounds on F or bounds on the mass, and these are equivalent. I will focus in this talk in this range of F around above 10 to the 6, 10 to the 7 GeV up to 10 to the 9, 10 to the 10. So this red band here, which corresponds to quite high masses. And yeah, this is the standard dark matter window. We are just below in terms of F. Okay. Remember also that all the constraints that you see in this plot, for instance, are actually based on individual couplings. Let's say the coupling not with the gluons, but with the electrons or with the photons or sometimes with the nucleons. And so they are expected to be 1 over F, but actually they are model dependent. So one has to be careful in interpreting this window. So the focus of this talk, as I said already, is that axions can act as background of relic particles. One may call them also dark radiation. And this happens if their mass is very small. And this is actually the window that we are looking at. And smaller than electron volt, because this is the typical mass that is corresponds to a light particle for the CMB, to a relativistic particle. Okay. So I will consider an effective Lagrangian for axions, and with the following rule: it can couple with essentially any standard model particle, as long as there is a continuous shift symmetry respected for the axion. The only breaking of this symmetry is the potential that I showed before, but that is a non-perturbative effect. Right. So, well, let's go first. The essential coupling that we need is the coupling with gluons. And this has been studied already from these papers. And it has been found that one can produce at very high temperature, can produce a background of axions, and it decouples at a given temperature, which I call T decoupling. Below such temperature, the axions are not in thermal equilibrium. One can estimate the rate of production via gluons just by looking at these diagrams. Is very simple because there is one vertex which is alpha strong over 2 pi f, let's say. So we have this factor square, and then there is another vertex which is G strong square. Okay, and then by dimensional analysis, if we compute a rate, it must go like T cube, because you have to compensate 2 powers of f in the denominator. Now this quantity has to be compared with the Hubble, and the Hubble goes like T square, so that's why this is in equilibrium at high temperature. Gamma is larger than H at very high temperatures. So how large temperatures? Well, for example, if I put F 10 to the 8, I get a decoupling temperature of a TeV. If I put 10 to the 9, I get 100 TeV and so on. Right? So what is the consequence of such a decoupling temperature? First of all, well, as we know, if a particle was in equilibrium above a given temperature and then it decouples below, it acts as dark radiation, as I said, and this will be observable in the CMB and also in BBN actually, because it affects the expansion rate of the universe around the CMB time and matter radiational quality as well, and at BBN as well. So traditionally, this is parameterized by an effective neutrino number. So just an additive contribution to the 3.046 of the standard model neutrinos. And now this is the essential formula. When a particle decouples at a given temperature, G T dec, okay, then the abundance is suppressed by the total number of degrees of freedom at that time. So as we know, G star is very large at high temperature, therefore delta N effective is suppressed. For instance, we saw a TeV scale, delta N effective is suppressed by the total number of degrees of freedom of the standard model. Therefore, this gives a small contribution. This gives, well, essentially it gives this number, 0.027, if you put G star over 106. Now you can observe that G star, well, as you all know, G star goes down at lower temperatures. And therefore, if one finds a channel that decouples at lower temperatures, this would be better for observability. Moreover, you know, when you decouple above a TeV, the number of degrees of freedom could be even much higher than 106. We don't know. Therefore, this is only an upper bound, okay, for the one for the gluon, from the gluons. And now this is marginally detectable by future experiments, in the sense that the so-called CMB stage 4 experiments, they have a 1 sigma sensitivity close to this number, but this is just 1 sigma. You need more than that, right? Okay, so now if instead you consider now coupling to quarks and leptons, this has been done in these papers here. In some models, the axiom couples at 3 level to quarks and leptons, right? So such as the DFZ model, for instance. If this happens, I will show that the decoupling temperature could be below the electroweak scale, right? So let's see why. Well, first of all, well, let's see what is the consequence. First of all, since G star is smaller below the electroweak scale, we can have a larger N effective. Moreover, we are somehow confident of what is G star in this range of temperature because we know the standard model there. Therefore, we can make precise predictions. And this is a big advantage, and not just upper bounds. And moreover, we will work actually at lower F, and this is actually accessible also by direct searches, such as YAXO or CAST. Okay, so how the typical coupling of the axion to the quarks, for instance, is derivative coupling. Now, the scattering rates can be represented in this way. You have 2 quarks producing, for instance, a gluon and an axion. Now one can estimate, first of all, there is a property. If the mass of the quark is 0, the Lagrangian itself, the term itself vanishes actually, because you can integrate by parts. And by using the equation of motion of the quarks, you can see that this is 0. Okay, this is one way of seeing it. Or another way is to see it is that you can actually rotate away this coupling by chiral rotation. And therefore, so that completely disappears, but it actually reappears in the mass term of the quarks. Therefore, the vertex is actually proportional to MQ, right? So that tells us that the rate must be proportional not only to the coupling, which is C over F square, but also to the quark mass square, and also to the G strong, which is the coupling here. Now, this has to be compared with the Hubble rate, and now you see that this goes linear in temperature, while the Hubble goes quadratic, as I said. So this is actually important at low temperatures, and the lowest one can go is the mass, because below the mass of the quarks, there are no quarks around, therefore there is an exponential suppression. So by this is maximized, gamma over h is maximized around the mass of the quark. Now, by doing this is just the same formula. Now, the ratio peaks at these masses, and therefore, for a given quark mass, one can produce axioms. And you know, the quark masses are below 100 GeV, and therefore one can hope to produce axioms when G star is smaller. The range that you need to have equilibrium is below 10 to the 9 GeV. So you need 10 to the 7, 10 to the 8, 10 to the 9 GeV. Now this is partly in tension with some bounds, for instance, supernova bounds, but those bounds are actually model dependent, and also the supernova are not so precise, let's say. So and this range is also very interesting for direct detection. Now let me, and also for the so-called hints from stellar cooling, this is the same range. So let's show some plots. Now the prediction is that actually you can see this red region as a function of f in the horizontal axis. You can see what is the delta n effective which is produced. And instead of being 0.027 is actually, let's say, could be 2 times larger, 0.03, 0.04 by different channels that I'm not discussing in detail. This has been produced by solving Boltzmann equations. And now a factor of 2 here is important because the sensitivity now could be, I mean, the signal could be twice the noise of the experiment. And this could be almost enough to detect it, while in the previous cases it was not. Okay, then, okay, I already mentioned this, sorry. The same, it could be even, so the previous plot was for B quark and for top, but now there is even the C quark. The C quark could even produce a larger N effective. These are, these green curves would correspond to the C quark. Now, there are many curves because we don't actually know what happens close to the QCD phase transition. The mass of the C quark is close to the QCD phase transition, therefore, this, there is a big uncertainty. Okay, so that's an interesting thing to look at. Okay, then the same can be done with leptons. One can use mu and tau, for instance, and the same, exactly the same calculation, it picks at the mass of the leptons now. Okay, so from the leptons, for instance, one can get from muon scattering this type of curve. It goes to much larger delta N effective, but it is at the lower F, and this is in contrast with some bounds from supernova. Sorry, yes, from supernova. But one can also look at decays, not just scatterings, because in some axiom models, the coupling could be off diagonal in flavor. Therefore, for instance, the tau quark could decay, and that gives a larger signal. Sorry, this is moving too much. And the same thing of these flavor non-diagonal effects could be obtained actually with the top. For instance, the top quark decays into C and axiom, and that actually goes to larger F. So for 10 to the 9, even 10 to the 10, you get a signal. Okay, finally, we studied also the axiom Pion coupling, which in the literature has been studied widely. However, in the literature, essentially all the literature has been focused on the KSVZ model, where there is no coupling in the two standard model fermions, while we focus on the DFSZ model. And because of the coupling to the U and D type quarks, there is a coupling to pions, which depends on a parameter. In the FSZ, it's 0.12 plus this contribution, where beta is the ratio of the 2 Higgses which are present in this model. So there is a parameter which has not been considered before. And now we put some constraints from present CMB data on the axiom mass. So you can see it has to be below 0.7, 0.8 electron volts, depending on this coefficient, the coupling to pions, which is not fixed in this model. Right. And finally, for the FSZ2, which is a different variant of the model, there is also production from muons. Okay, this is maybe a detail. An important caveat has been pointed out by this recent paper is that actually Pion cross sections, the standard calculation which has been used so far in the literature should actually break down at already at these temperatures. So that is a big caveat. And then let me just show the conclusions. Conclusions are that efficiency peaks at the mass of the fermion. For quarks, an effective is less than 0.05, but it could be 0.04, 0.05. For leptons, it could be up to 0.3, for instance, from tau decay. And finally, there are also decays from non-diagonal couplings, such as quark decay, and this could go up to 10 to the 10 in F. Let me also mention that a largish and effective can also alleviate the H0 tension, as you probably know. And so this could be related to this physics. And finally, Pion production puts a bound, which is actually of this size, 0.6, 0.8 electron volts for the FSZ axiom. And that's it. Yeah, future experiments will tell in a few years if this is realized.
Thank you for nice talk. Okay, so is there any questions or comments? So then let me ask first just a basic question. So you discussed the coupling between axion and quark and lepton, and is there any contribution from axion coupling to Higgs or axion coupling to weak gauge bosons?
Yes, there is. So to Higgs, this has been studied. However, there are two problems. First of all, one can actually rotate away the couplings to the coupling to the Higgs, the direct coupling axion Higgs, but then it reappears in the Yukawa. So it's always there, actually. However, this is important only at very high temperatures because the Higgs is heavy, and therefore this will affect only marginally delta N effective. So it cannot be more than 0.027 at those temperatures. And the same for the gauge bosons, because since they are the heavy ones, they only affect the production at high temperatures. And finally, well, except from gluons, which has been studied, and photons, but photons are subdominant compared to gluons.
Okay, good. So any other questions, comment? Okay. So then, yeah, well, one more related question. So in this study, so you basically assume some QCD axion example, right?
Sorry, some QCD axion?
I mean, not some general axion-like particle, but you are thinking some QCD axion production, hot QCD axion production.
Yes, but it would be similar for any axion-like particle as long as the mass corresponds to a relativistic particle, so less than 0.1 electron volt or electron volt. Okay. If the mass is a little bit larger, then one should run a separate analysis with the CMB code, because then it's not a hot relic anymore. It's like something like warm dark matter. And therefore, one has to run a code. And indeed, this is what we did for this. So let me go to the previous slide. In the case of the FSZ, we also included the mass in the effect. It's not just the abundance of a relativistic particle, because the mass is actually, you can see from here, it's close to being non-relativistic at CMB time. Therefore, yeah, but that would be essentially the only difference.
I see. So then if we consider, for example, KB mass scale, then is it also can be warm?
KB, yes, that would contribute to dark matter. So to warm dark matter would be a warm dark matter component. However, the abundance is very small compared to the cold dark matter component. So I would suspect there is no bounds.
Okay.
Yeah.
Okay, I see. So I couldn't see any other questions. So then let's thank the speaker again, and let's move on to our last speaker of this session. Okay, Jim Aronson, right? Is it correct?
Yes, correct.
So, okay. So our last speaker then talk about the fragmentation of the action field in the early universe. So please start.
Okay. Are you seeing my full screen, right? Okay. First of all, I would like to thank the organizers for providing the opportunity to give this presentation. In this talk, I will tell you about fragmentation of the axion field in the early universe. So the impact of fragmentation on the axion dark matter parameter space has been explained quite well with Philip Sorensen, who is also one of my collaborators in this project. The other collaborators are Yusuke Sato and Geraldine Sarwan. Both, all of them are from DAISY. Philip already talked about the misalignment mechanism, so I will go quickly over it. So when the patch-equine breaking happens during the inflation and each Hubble patch gets a random value of the initial angle theta I, the inflation inflates all the Hubble patches quite rapidly. So therefore, in the end, in our observable universe, we see an almost homogeneous axion field. Because of this, the fluctuations of the axion field are usually neglected when solving the cosmological evolution. So we treat the axion field as a background field which depends only on time or analogously to temperature. When we solve this equation with initial condition where the initial kinetic energy is neglected, is 0, then what we see is the field is initially Hubble frozen due to the strong Hubble friction, and later it redshifts as a⁻�3, which implies that the axion energy density redshifts as matter. And the transition between these two regimes happened around the time when the temperature-dependent axion mass becomes the same order as the Hubble scale. And then the Rayleigh density, as Philip told you, the Rayleigh density determined by the initial angle and the oscillation temperature where this equality is satisfied. Now, this is the pure classical picture. All the fluctuations have been ignored. When you include the effect of the fluctuations, what you find is the fluctuations become important only when the initial condition is very, very close to the top of the cosine potential. This effect has been studied initially in this paper, and a very detailed recent study can be found in this paper where the authors called this the large misalignment mechanism. The reason why the fluctuations become important in this model is as follows. If you tune the initial point very close to the top, then this delays the onset of oscillations. Therefore, the amplitude of the oscillations decay at a much slower rate because the effect of the Hubble friction is smaller at late times. This allows the axion field to probe its non-quadratic part of the potential, and this yields to parametric resonance, and you create some axion fluctuations. Even though this looks like a tuning at the first place, there are also some mechanisms which can make this apparent tuning more natural. But there are other possibilities where fluctuations can become important, and one possibility is the axion has a large initial kinetic energy, which is much larger than the barrier size, so that the axion travels many barriers before it gets stopped in one of the minima. This can arise in two ways. One possibility is axion receives a kick from explicit patch-equine breaking in the UV, as explained by Pira. And the other possibility is the recently proposed trap misalignment. And in this case, the axion potential has two regimes, the high temperature regime and low temperature regime. First, the axion starts to oscillate around the high temperature minima, and then phase transition happens. And as the axion field rolls down to low temperature minima, it can gain a large kinetic energy. the effect of the fluctuations in this model has been throughout studied in these two papers, both of which are also from the DAISY group. And what they have found is that the modes which lies inside the instability band given by this expression and experiences exponential growth while the axion field is rolling through the barriers. So this instability band moves through the momentum space as the axion field rolls. And this movement happens from larger momenta to smaller momenta as time goes on. Therefore, you amplify higher momenta first, and then you amplify lower momenta later. Now, in a nutshell, the whole procedure works as follows. So here on the horizontal axis, we see the axial velocity. As time goes on, the axial velocity will decrease due to Hubble friction. So there we start with a high velocity in the beginning. And in this regime, as Philip also mentioned, axion rolls too fast for particle production. So the time a momentum mode stays in the instability band is very short. Therefore, there's no enough time so that this momentum mode grows exponentially. Therefore, we don't have any fragmentation in this regime when the axial velocity is high. Then there is the middle regime where the particle production starts to kick in, but the dynamics is still dominated by Hubble. What I mean by that is the back reaction of the fluctuations on the homogeneous mode is very small, therefore can be neglected. Therefore, the dynamics of the zero mode is still determined by the Hubble parameter. But this particle production will be more and more efficient as the axion velocity drops and also the Hubble scale drops. And at some point, it starts to increase quite rapidly. And at some point, the back reaction of the fluctuations will on the homogeneous mode will be so strong that this back reaction stops the axion field from rolling, and the axion stops at one of the minima. So here I show how much a momentum mode grows as a function of a rescaled momentum variable. So it's convenient to rescale the momentum modes, which the axion mass at the time of trapping. So you see that the higher modes are amplified during the period of weak fragmentation. So in this case, the back reaction of the fluctuations on the zero mode is small, but we have an exponential growth. And at some point, the fluctuations become so strong that they start to back react on the homogeneous mode. And so then the amplification sort of saturates due to the strong back reaction. So how is the evolution of the axion energy density in this model? So initially, the axion field is dominated by its kinetic energy. Therefore, the energy density scale is like kination, so (8⁻⁶). Then on this line, fragmentation happens. And since the modes which are produced are slightly relativistic, the axion field redshifts for a short while as radiation. Then after the redshift, all the momentum modes which are amplified becomes now relativistic, and the axion continues to redshift as matter, and eventually can make all of the dark matter today. So the axion field is trapped when its kinetic energy becomes comparable to the potential energy of the barriers. And this happens approximately when the time derivative of the angle becomes comparable to the axion mass. And what I mean by T star is the temperature at which this equality is satisfied. So there are two possibilities here. One possibility is the possibility that I already told you about. So first, the fragmentation happens, but the effect of the fragmentation is small. So the evolution of theta dot with and without back reaction coincide. But at some point, strong fragmentation kicks in and the axion field stops rapidly due to the back reaction. But it is possible that this strong fragmentation regime is not activated. What happens instead is the axion trapped by the potential barrier before this strong back reaction regime starts to kick in. So in this case, the fragmentation will not be complete before trapping, in opposite to this case. But even in the absence of fragmentation during rolling, this still delays the onset of oscillations. So in the conventional misalignment mechanism, the oscillations start when the axion mass becomes comparable to Hubble. But in this mechanism, so which is also called kinetic misalignment mechanism, the onset of oscillations are delayed compared to the standard case. So therefore, we have the same effect as the large kinetic misalignment mechanism, where you tune the initial angle to the top. Since the oscillations are delayed, the amplitude of the oscillations decay at a much slower rate compared to the standard misalignment mechanism, and this can lead to efficient fragmentation after trapping. So we can even calculate this effect semi-analytically. And what we have, if we do this, what we have found is as follows. So here I'm showing the ratio between the number density in the fluctuations and the number density in the zero mode. And what we have found is this quantity is proportional to the axion mass at trapping temperature over F, and this quantity is squared. So we have a large suppression from this factor. But we have also an exponential enhancement from these two, from the axion mass at trapping and Hubble at trapping. So even though this quantity is quite small, if there's a hierarchy between the axion mass and Hubble at the trapping temperature, then this exponential factor can easily overcome the suppression coming from this term, and we can have order 1. So the number density in the fluctuations can be order 1 compared to number density in the zero mode, which means complete fragmentation of the axion field. So I will remind you the plot that Philip has already shown you. So in this regime, above this blue line, fragmentation is active before trapping. So this is the first model mechanism that I talked about. And between the blue line and the purple line, the second mechanism is active, and the fragmentation completes after trapping. So what are the observational prospects of this mechanism? So this is still a work in progress, so I won't be able to show you concrete results, unfortunately, but we have some good understanding of what we can expect. So when you calculate the power spectrum of axion fluctuations right after the fragmentation, what you can find is for some modes, which for the momentum modes, which are at the order of the axion mass at trapping, the power spectrum becomes order 1. So these fluctuations will evolve during the radiation era, and when they reach to a critical density, which depends on the redshift, they experience gravitational collapse. And this gravitational collapse can be understood in terms of the Press-Schechter formalism. And what you see is, so when the variance of the fluctuations smoothed by a window function reaches to a critical density, they collapse gravitationally and form from gravitationally bound halos. So the density of this halos is proportional to the dark matter density at the time of collapse. Therefore, if the collapse happens earlier, then they lead to much denser dark matter halos compared to CDM or standard misalignment. And that's one way of proving the fragmentation. Yes, these are my conclusions. So what we have found is a large initial kinetic energy of Axiom fluctuations can play a prominent role and can yield complete fragmentation. In some cases, the fragmentation becomes effective before the axion gets trapped by the potential, in some cases after the potential. And so, and this fragmentation leads to much denser dark matter halos. And finally, let me say that this discussion is applicable to QCD axiom, a generic alt model, as well as other kind of potentials such as monodromy. Thank you very much for your attention.
All right, thank you for your nice talk. And so this is the last session, so maybe audience can have more questions if you have. All right.
So I have a question. So what? Hello.
Yeah, go ahead.
What is the size of this order 1 fluctuations compared to the horizon at that time?
They are smaller than the horizon because the momentum modes which are amplified are well sub-horizon.
Okay. Yeah, I was asking because I was thinking of maybe having primordial black holes from that, but maybe it's difficult. Have you thought about that?
No, we didn't consider primordial black holes.
Okay.
But I expect they should be smaller than the horizon size. So. But thanks for the suggestion. So.
Other questions or comments? Yeah, I think there is one question from Feng Li.
Hi,
So
Sam, can you hear me?
Yeah, we can hear you.
Okay, yeah, nice to meet you again. Well done. So here I have one stupid question, maybe just related to what happened to those super horizon modes. Like say, can you really predict their production compared to the tradition, just the standard misalignment? Is that just or it's just trivial?
Super horizon modes are not affected by the fragmentation.
So there's no way.
So
there's no way to change their or maybe there's a way, right? Or there's like by definition there's no way.
Okay, so I should say okay, so our calculation relies, so our calculation was semi-analytical. So, and after some time, when the fluctuations become order 1, our calculation breaks down because the field does enter to non-perturbative regime. And since the smaller momentum modes amplify at a later stage, this corresponds to the time at which non-perturbative methods should be used to really predict what happens to this mode. So maybe after proper lattice simulation, we can understand how these modes should behave. But so probably smaller super horizon modes should approach to CDM line. At least that's what have been found in this large misalignment mechanism. So lower momentum modes corresponding to larger halo masses, they sort of merge to the CDM line. So therefore, I expect that the super horizon modes are not affected by the fragmentation. So
thanks. That explains everything very well. Thanks.
So maybe if there is one more question, we can ask.
Sure.
Okay, I think there is no more questions. So then, yeah, let's thank speaker again. Okay, good. So yeah, we finished basically all talk in this session. But before finishing this session, I have just short announcement. So after nearly 30 minutes break, we'll have the plenary session about neutrino oscillations. So anyway, thanks all speakers and audience for your contribution to this session. Okay, so let me finish. Thank you.